So last time we introduced the notion of event, then the notion of the set of events that we want to consider, and to give some concreteness, because those were abstract definitions. So we introduced the elementary events. And we put them together in a set omega, which is called the sample space. In this way, we could model events as subsets of the sample space. So this is basically what we did last time, and this time we will introduce what probabilities are. So recall that the aim is to associate to each event, so to each E in this set F, we want to associate a number which is the probability of this event E. So this number must be in between 0 and 1, and the meaning of this number is the likelihood of E. So the bigger is this number, the more likely is this event, whatever this means. But in many cases, it is intuitive. So in practice, therefore, the probability is a function that goes from this set of events that we want to consider in 0, 1. So, and which associates to each event this number. Sorry. So not every function is not every p is has the right to be called a probability. So there are some constraints to be called a probability. So to be rightfully a probability. And these constraints are, for instance, just an example. So if E is contained in F, then it has to happen that the probability of E is smaller than the probability of F. For instance, if E is like tomorrow it rains, and F is sorry, if E is tomorrow it rains heavily, and F is tomorrow it rains, of course the probability of the first event is smaller than the probability of the second one, because if the first one happens, also the second one happens. So not every function, not every number associated to each event is a good probability. So let's see what there are some conditions that P has to satisfy. But I won't give them in the full generality simply because it is a little bit technical and we restrict to sample spaces of the finite sample spaces. So I could go on to define, to introduce the Kolmogorov axioms, but I won't do that because they are too technical, and maybe I will do it later. They are technical, and we are restricting to finite sample spaces of the form omega 1, this form here. So it is much, in this case, the Kolmogorov axioms, they are too easy to be stated. So it is better simply to, the following, in the following, we will restrict to finite sample spaces. So the chapter here is probabilities on discrete spaces on finite sample space. Well, so first of all, in this case, so let's start from an omega. Let me repeat that is of this form. So what are the events we want to consider? We want to consider, basically here we can choose every subset of omega. So the events we want to consider are the following, are simply A, where A is a subset of omega. So every subset you can come up with is an event that you may want to take into account. And a probability is a function from this set F to the numbers between 0 and 1. So how can we define it? So let's start by defining, the probability on elementary events. So we start so for instance, we have n elementary events, so we have to define n numbers. P1, which is the probability of omega 1 that happened. Okay. Well, so we have to define the probability of omega 1 and omega 2. Okay. Here. So the probability of omega 1 is denoted by P1 and etc. etc. So Pn is equal to the probability of omega n. So here we can choose these numbers quite arbitrarily. We have only two conditions that we have to impose. So basically is that Pi is in 0 and 1, this is because they have to be probabilities, and the only other constraint is that P1, the sum of these PIs has to be equal to 1. Well, why? It will be clear later, but is because we want to say, so this second condition, as will be clear later, this second condition means that every outcome, for sure, an outcome in omega will happen. So we did not leave out anything from this sample space. So let me put this into a definition. Like a probability on the elementary events of omega is a set of numbers P1 Pn satisfying Pi is in 0 and 1 for each I that goes from 1 to n, and as I said, that the sum has to be equal to 1. So this is, I mean, this is quite intuitive. And then how do you define a probability of an event? Well, now the probability of the events, of each event is determined by these numbers. So the probability of each event is determined by the probabilities of each elementary event. So, for instance, I don't know, let me do an example. Yes, let me do an example, and then to give the definition. So the example is like a die has been rolled. So the sample space is this one. And let's take an event. Let's take two different probabilities. So so one is the probability of a fair die. Our P1 is equal to 1 over 6, which is equal to P2 equal to all the other ones, which is equal to P6. So, I mean, is it clear why this is the probability of a fair die? Because every outcome is equally probable. So there is no phase of the die which is more probable, is more likely to arise. So every it's like a symmetric die. So every every outcome is equally probable. This is if it is balanced, but it can be rigged. I mean, there are some die that are like fake, and they have different probabilities. So for a rigged, an unbalanced die that I don't know, we can place here random numbers. Maybe Q1 is equal to 1 over 8. Q2 is equal to 1 over 8. Then Q3 is equal to Q4, is equal to Q5, is equal to, I don't know, let 1 over 5. No, it's 1 over, let's say, 4. And then, no, this is 1 over 1 over 16. I didn't want to make it to spend too much time in computing sum, but this is Q over 6 has to be equal to this is 3 over 16, this is 2 over 16, 4 over 16, 9 divided by 16. So this is an example of an unbalanced die. And now we want to compute, for instance, the event that the result is an odd number, which is equal to 1, 3, 5. So, well, the first probability is so this event computed if the die is balanced is simply the sum of the probabilities of getting 1 plus the probability of getting 3 plus the probability of getting 5, which is equal to P1 plus P2, P3 plus P5, which is simply 1/2. Why? For the other one is the same. I mean, the procedure is the same, but now the numbers are different. So it's the sum of the probabilities of getting 1, 3, or 5, which are the elementary events that compose A, and this is equal to Q1 plus Q3 plus Q5, which is equal to 1 over 8 plus 1 over 16 plus 1 over 16. And this is a number which, what is a number? But the procedure is clear. So we take an event, we see, we look at the elementary events that compose this event, and then we can compute the probability of this event. So let me give a definition. So the definition of probability associated to the probabilities of the elementary events. So let's take a probability on elementary events So let P1, Pn be a probability on elementary events, its associated probability must be P, so this range P is a function that goes from the events to 0 and 1 as before. So that to each event associates a number in the following way. So from an event E, it gives you a number, the probability of E, defined in the following way. So we have to take if E, so defined by the following formula. So the probability of E is equal to the sum of the over the events, the elementary events that are in E, of the probability of the elementary event omega. So in words, the probability of E is the sum of the probabilities of the elementary events that compose E. Um, to be more to be more less abstract, if E is of the form is has the following expression. So a general event can be written in the following way. So we take omega E1 omega ek. This is a subset of omega, and its probability is simply the following. Omega, the sum of omega I1 plus the sum of the elementary events that compose E. So the sum of P omega I1 plus P omega I2 plus P omega I until P omega I. So and this is how the probabilities of the elementary events determine the probability of an event. So this is quite basic, but has to be. I mean, I hope it is clear for everybody. So okay, for instance, if omega, I don't know, to get familiarized with the notation, so to get used to the notation, let's make an example. So if we take two coin tosses, we have the following sample space. And let's take the event E equal to the second toss gave 1. So this is clearly the event, well, is the, so can you, so the question is to specify, for this case, for instance, omega, to specify the numbers which were placed here. So n omega 1 omega n k, the k is this k here of the event E, and also I1 ik. So in this case, for this event E, what are these numbers I1, ik, what is k, I mean. So maybe I can give you like 5 minutes to do this exercise if you agree, or if you, I mean, if it is easy, I can go on. So if you already did, I mean,
1 minute, just maybe.
okay, yes. Let's wait 2 minutes. Okay, maybe I can correct it. So it is simply, well, in this case, n is equal to 4, because there are 4 elements. Then omega 1 is equal to 0, 0. Omega 2 is equal to 0, 1. Omega 3 equal to 1, 0. And omega 4 is equal to 1, 1. E, which is the event, 0, 1, 1, 1, well, it is equal to omega 3 and omega 4. So in this case, k is equal to 2, I1 is equal to 3, and I2 is equal to 4.
Just a sec. The omega 3 is 1, 0, and it does mean that the second does give 1. So maybe omega 2 then.
Ah, thank you. You're right. Then I1 is equal to 2. Perfect. So this is simply I mean, it can be a strange notation, but a general event can be written in this way. So you take a subset of indexes of one, so I1, Ik is a subset of the indexes 1k. So in general, okay, let me write it here. So in general, 0 is greater than A1, which is greater than A2, which is uh, sorry, which is smaller than AK, and AK can arrive up to n. So I1, Ik are a subset of indexes, and in this way you can write a general event. So okay, this is I mean, this is simply to get used to the notation. So now we can give a bunch of examples. So the first the first important example is the uniform probability. So which is what you expect. So when you have no preference on the outcomes. So uh, when there is no preference, there is no there is no favorite outcome. We so it means that each outcome is equally probable. So let's take again omega is equal to omega 1 omega n, and p1 is equal to p2, which is equal to pn, which is equal to a certain number c, let's call it c, which is in 0, 1. Now, how can we determine c? Well, um, we have the condition that p1, that the sum has to be equal to 1. So we have this condition. Well, on the left-hand side, you have that P1, so P1 plus Pn is simply the sum of C n times, which is equal to n times C. So in practice, we have that 1 has to be equal to n times C, so that C is equal to 1 divided by n. Therefore, each outcome is equally probable and has this probability. So pi is equal to 1 over n for each I in that goes from 1 to n. So we have made an example of this probability, which was the fair die. We made an example with n equal to 6, the fair die. So what is the probability of an event in general? So the probability of an event t, if e is equal to omega I1 is a set of k elements indexed by this A1, AK, then the probability of E is equal to, well, to the probability of the elementary events that compose it. So it's equal to the probability of omega 1 plus omega I1, sorry, plus the probability of omega ik. But these probabilities are all equal to 1 over n. So this is simply the sum, n times the sum of 1 divided by n plus etc. So each elementary event has the same probability, so there is no, these are all the same, always the same number, k times. So this is simply k divided by n. Okay, so do you have questions on these computations? So there are an event which has k elements. So in practice, each event that has k elements, k elementary events, contains k elementary events has the same probability, which is k divided by n. So in other words, this is called uniform probability. So let me put it into a definition. So, and let me put it into a fancy way. So let omega be the sample space, let omega be a finite sample space, and denote by this module the number of elements uh, of a set. So in particular, the number of elements of omega is equal to n, for instance, can be written in this way. So using this notation, this is the uniform probability can be written in a fancy way, which is the following: the uniform probability over E, sorry, over omega is the probability measure, the probability that assigns to each event E the probability well, the following probability. So what is the probability of E? Well, is K divided by N, but K is the number of elements of E. N is the number of elements of omega. So we can write it in this way. So this is like the number of elements of E divided by the number of elements of omega, and yes, and this imposing that each elementary event has the same weight leads to this expression here, and so computing probabilities in this case, in this uniform case, computing probabilities is the same thing as counting. So which is actually not easy, because I mean, probably you have seen that they appear, a lot of stuff appear when counting elements, like binomial coefficients are kind of the simplest objects, but in general, when the sample space is large, you cannot really count. For instance, when you do a chess match, because I mean, usually things grow too fast to be computed. So, and but in principle is simply counting. So, and in general, computing probabilities is like counting with different weights. So, so, but by no means it's simple. So this is the first probability, which is kind of really, I mean, is like the prototypical, which and prototypical example, and usually is so important this example that maybe sometimes it is like it is assumed that this is the definition of probability. It is not. Uh, but there are some examples like, well, the fair die, we did it, but like random so the next example is the one of random extractions. Uh, like random, so, and randoms goes between commas, because what I mean, like well, let me state what these extractions are. So we have a population of n individuals by random extractions, and okay, let me denote these individuals by I don't know, well, by omega. Let me do a slight abuse of notation, and let me denote the individuals as the sample space, as with the same letter. So omega 1, omega n is this population. By random extraction, we mean that omega I is extracted with probability 1 over n, so with uniform probability. Like this is the typical, I mean, it is really, really difficult to do something like this in practice. Like you would like to, I don't know, when you do a poll, you want to extract, to call randomly as uniform as possible to extract a person from a population. But for instance, if you call people at home, you are assuming you are doing like an extraction from people which have a phone. Now, maybe it's not an issue, but in the past, not everybody had a phone, and many polls went really bad because they were sampling not from all the population, but from a particular subset of the population. So the problem of having this extraction as uniform as possible is really a problem in statistics. In this case, what I want to point out is that random is like a word here is used to say that the probability is uniform, but actually also like I don't know, when they choose the Nobel Prize, they choose randomly, but not uniformly at all. They have some candidates, and there is some randomness there because there is some choice to be made, but it is not at all uniform. So here, random has the meaning of uniform, but every extraction is random, also with not a uniform probability, maybe. So this is an example. Then there is, well, the other examples are the usual ones. Like extractions with replacement, with or without replacement. Um, so you did an exercise which was quite easy about like the sample space of extractions of balls. So you can think that balls are individuals and do the same stuff. So let me denote the sample space of extractions with replacement. From n individuals of two extractions, let's say. With replacement, let's say, which is the following. Well, is the set of pairs omega I, omega j, where I and j vary from 1 to n, because there are n individuals. And omega I, let's say omega I omega j means that the I individual has been extracted in the first extraction, and omega j in the second one. So here I'm making a mess with the notation, because here the omegas are not the elementary events, so I should call it maybe let's say A1, A1, AJ. So mm, so when they not the if individual, but the individual AI has been extracted in the first extraction, and the individual AJ in the second one. And here, since we don't have any preference, any preference is, I mean, is expected. It is to be expected. We don't want to have preferences on the pairs, so we expect to put here the uniform probability. So we place the uniform probability. Uh, so this is an example, and we will see in the next lecture that the uniform probability here is implied by two properties, which are the independence of the extractions and the uniform, the random uniform, and that each extraction is uniform. This is something that we will see in the next lecture, but it is quite intuitive that each outcome is equally probable. So instead, without replacement, well, omega is simply equal to the set AI AJ, where I is different from J. So where I and J go from 1 to n, but I is not equal to J. It's different. So since we cannot extract twice the same individual, and again here is the same the same comments hold. There is no preferred outcome, and the uniform probability is the right one. Do you have questions on these examples? Do we need to repeat something? If not, I go on. If I mean, this is a good moment to ask questions, uh, if any. Otherwise, I go on. Uh, well, okay, maybe let's do an exercise, and then after we correct the exercise, and then we make a pause and pass to the to define the conditional probability, and this actually leads to more interesting examples, like some kind of paradoxes, which are not really paradoxes, but counterintuitive facts. So let's make an exercise, maybe, so I find it. So yes, I have it here. Um, Okay, yes. Um, okay, collector. Ah, by the way, I wanted to ask you, did you take any course on the R programming language like RStudio, something? Do you know how to
We had an
program?
introduction this September and October, like 4 or 5 classes.
Ah, okay, perfect. Maybe, of course, in the next module, we will basically do every lecture in Honor Studio. But now, maybe since I have some more lectures that I didn't expect to have, maybe we will see something more practical. So, okay, thank you. Um, okay, now let's do this exercise, which is the exercise number 2. I can send it. I will put it later on the chat now. Maybe okay. Maybe 15 minutes. It's a good time to. It's a good uh, the right amount of time to do this exercise. I don't know. Let's see. I will be here. So if you have any question, just write me or and see you otherwise in 15 minutes and we will correct this exercise. So do you need more minutes or can we correct it?
I think I could explain in words because typing it it's too hard. I can explain the words of the first exercise and maybe try the second, but only the first part.
Okay, yes, yes, sure.
So we should define as A1s as all the omegas that satisfy us, all the omega i's. And we know that among those omega i's, there will be also those omegas that satisfy for the event A2, as it can be that 1, 2 are on their places, while 3 and 4 are somehow arranged differently. Um, thus, counting the probability of their union, we need to subtract um, the additional probability that we got when we summed those omegas 2 times, and that's exactly the probability of their intersection.
Yes, exactly. So this minus here account because we are overcounting some events. So yes, the events that are both in A1 and in A2 are counted twice. Yes, that's correct. Maybe then after that, maybe I will write it like what these sets are precisely. But the idea is exactly this one. Yes.
And for the first part of the second exercise, second part of the exercise, we have n numbers, n symbols. Yeah, we have n symbols, and the intersections of A1, A2, A3 are just 1 minus 1 symbols in their places. So there is only one place for the nth element, and that's exactly an omega that belongs to A4, a nth.
Okay. Yes. This is yes A4. Yes. Yes. And here is 4. Yeah. Yes. And okay. Yes. And the last one we will do it now. Okay. That's correct. So let me go back to the lecture. So, okay, so first, as you said, well, first, simply to fix the ideas, let's fix some omega. This is equal to a rearrangement of these four numbers would be something like sigma 1, sigma 2, sigma 3, and sigma 4, where each sigma I uh, is in 0, sorry, is in 1, 2, is either 1, 2, or 3, or 4, and each sigma is every sigma is different. So, and sigma I is not equal to sigma j if I made a mess. If I is not equal to j. So if the sigmas are different, also the okay, what happened here? I don't know. Yes. Okay, so this is the set of possible rearrangements of these four numbers. If one wondered how to put it formally, but yes, A1 is equal to all the possible rearrangements that starts with 1. So sigma 2, sigma 3, and sigma 4, where again sigma I is not is in is either equal to 3, 2, 3, or 4, and sigma I is not equal to sigma j if I is not equal, if I is equal to, is different from j. So is the same as above, but one is fixed. So basically, yes, as you said, if you count A1, A2 is the same stuff, but with a fixed 2, so 1, so sigma 1 to sigma 3, sigma 4, and I avoid writing all the other part of the A2. So yes, if you want to compute the probability of A1 union A2, so A1 or A2, we have to count the number of elements in A1 and A2 divided by 24, because there are 24 elements in omega. So this is the definition of uniform probability. But so counting the number of elements in A1 or in A2, what do we do? Well, we can simply sum the number of elements of A1 plus the number of elements of A2, but here we are overcounting. So why we are overcounting? Because there are some elements which belong either to in both A1 and A2. So this is not, this would be correct if there were no intersection, but there is some intersection. So A1 cap A2, and we are overcounting these elements twice when we sum. So we rely on this formula here, and we substitute this equality here. So we write um, so this is an equality that we obtained, we can obtain theoretically. So it holds for every, we didn't use the fact that the sets have had this form. In this case, we can verify this equality. So let me simply state that A1 has a number, how many elements does A1 have? Well, we have to arrange three terms, so it is 3 factorial. Yes, sorry, I made a question and replied myself. So
Yeah, sorry. Okay, yeah, I didn't know that it was
no,
um, uh,
no, actually, okay, but it is. Do you agree that it is 3 factorial?
yeah, which is exactly 6. Yeah.
Ah, yes,
Yeah.
it is. Okay. Ah, okay, sorry, I didn't get it. Okay. Then, well, A2 for by symmetric, so A2 also is equal to 6. And A, um, A2, A1 intersected with A2 is equal to, well, to 2, I guess. There are only 2 elements. This set is equal to simply to the set to these 2 rearrangements. So to 1, 2, 3, 4, and 1, 2, 4, 3. So it has 2 elements. So we have simply to check that this set has a number of elements which is equal to 12 minus 2, 10 elements. So I mean, we could write. So I'm not sorry, I made an error. So maybe I don't know how much time it will take, but this set is equal to, okay, 1, 2, 3, 4, 1, 2, 4, 3, 1, 2, 1, 4, 2, 3, 1, 4, 3, 2, sorry, 1, 4, 2, 2, 1, 3, 4. No, this is not in the set, sorry. 1, 2, 4, 3, 1, 4, 2, 1, 3, 4, 2, 3, 1, and I guess I'm forgetting 3 elements, which now I maybe 3, 2, 1, 4, 3, 2, 4, 1, sorry, 3, 2. And the last element that I'm forgetting, probably 1, 4, well, I'm forgetting an element, but it should be it should have 10 elements. I mean, it's not really deep this exercise, so maybe you can, if you are interested, finish it by yourself. Maybe let's do some 15 minutes break, if you agree. Okay. And in the meantime, maybe I finish also this exercise. So see you in 15 minutes. Any questions? If you don't have any question, otherwise I'm here. So maybe let's come back to the lecture. I have actually put the exercise in a correct way because maybe it was important to solve it correctly because it's a verification of a proposition that now I will state without the proof because the proof is basically this one. So let me be more precise. So we have this omega, which I have written. It has 24 elements, which I have listed here. Now A1 is the set of those strings which fix the first number to 1, to be 1, and A2, the second digit is 2. So they have both 6 elements, and these are here. So if I look at the union, so I simply have to merge the elements of A1 and the elements of A2, but then these two, the first ones, are repeated twice. So I actually, when I merge these two sets, I have to remove 2 of these elements because they are repeated. And so the meaning uh, of the formula that we saw before is that we are subtracting exactly what we are counting twice. So let me give some properties that a probability satisfy. So it is actually the most important properties are two, which are the following. Well, the first one is quite follows from the properties that we have imposed, which is the following: that the probability of the full sample space is equal to 1. So an element of the sample space will happen for sure. Why is that? Well, because the probability of omega simply equal to the sum of the probabilities of the elementary events that compose omega, which are simply P1 plus P2 plus Pn, and we have required that they sum 1. So this was a requirement. And this explains also why we did require this property. And the second proposition is the fact that the probability is computing a probability of an event is like counting. So let me this time state it in a precise way. So let omega be the sample space, and let B be a probability over omega. Whatever, it doesn't need to be uniform. However, that formula still holds. So still holds because the probability of the union of A union B is equal to the probability of A plus the probability of B minus the probability of the intersection, because we are counting it twice in the above sum, in the previous sum. So this is the for each event, for each A and B. in so these are the two propositions. The first one is proved. The second one is simply one has to reason, as in this case, and I will not prove it. Do you have any questions concerning the statement of this theorem, this proposition? Is it if it is clear, I go on, move on. Okay, perfect. So now I will start the topic of conditional probabilities. Uh, so yes, okay. We assume so. Um, of course, a probability is like changes when you over time, because I don't know, you see that an event happened and then you may want to change your degree of belief of an event, so the likelihood you with which you consider an event will happen. So probabilities usually depend on the state of information, and here we want to see how the probability changes if you know an event A. This is basically what we want to do now. Well, so this is quite so the way of if you observe A, it is really easy to guess what will be the new probability. So we observe A, or we know A, and we want uh, to define a new probability. So, and we start with a probability P. So we start with a probability P. We know that we then happen to know, because maybe we assume it or whatever, we know A, and we want to define Q in such a way that we want only using only the information we have from P, because we know P and we know and A, because these are the things we know. So how do we do that? So maybe let me try to draw some drawing. So let me share the board. So okay, okay, so we have our sample space omega, and we have our probability P that weights the elements here, and we observe A. So now the new probability Q, there are the elements omega that are here and the ones that are not in A, so this is A complementary. So the new probability Q will be, we'll have to assign 0 if omega is not in A, because we know that A happened, so it has to be equal to 0. And what about Q of omega when omega is in A? So, well, we may want to keep the proportions that P gives to us. So basically, what do? We would like to define it as P of omega. What happens if we do like that? Well, nothing, it is not a probability if we define it in this way, but not by too much. We don't do such an error. Why it is not a probability? Well, simply because the sum of Q omega 1, this sum Q omega 2 plus Q omega n is not equal to 1. So why it is not equal to 1? Simply because here we had before P, which weighted everything 1, but now we are simply setting P equal to 0 here. Q which weights P here and 0 here, so we are losing some mass. We are setting this to 0. So basically the correct way to do it is we define Q of omega equal to 0 if omega is not in A, and a constant C to be determined times P of omega if we are in A. Okay? So does it make sense? It's the only way in which you should define it. Why? Because you keep the proportions given by P, and you're simply setting to 0 because outside A. And basically, you have only these two information that I give to you. So it's the only reasonable way to define it. But what is this constant C? Well, we can compute it by imposing that Q of omega 1 plus Q of omega n is equal to 1. This we impose it. This is equal to C P of omega 1 if omega 1 is in A. So this is equal to the, it's easy to check that this is equal to the sum of omegas in A of P of omega times C, which is equal to C times the probability of A. So do you have questions concerning this equality? It is, I mean, it is a strange notation, but we are summing this Q is C times P if omega is in A. So we are summing only the omegas that are in A. And this leads to the probability of A. So basically C is equal to 1 divided by the probability of A. So basically, this new probability Q is equal of computed in omega is equal to 0 if omega is not in A, and the probability of omega divided by the probability of A if omega is in A. So this is the only way to define it, and Q, it is usually denoted in this way. Uh, the probability of something, here I put a dot because the events will go here. So if I have E, the probability Q of E is equal to the probability of E given A. But this A is a parameter, simply to remember that we are conditioning over A. So it is not, it is a probability on this first, if we fix A and we vary E, this is a probability. So that's why I've called it Q of E. And this notation keeps track of A. So this is the definition of conditional probability. So now probably you have seen it in another way. Well, let's take an event E. Let's take E equal to, I don't know, omega I1, omega I2, omega ik, and let's take A and assume like, I don't know, well, no, let's compute the probability of E given A. This is equal to the sum from I to K of the probability of omega I, sorry, ij, which is equal to the probability given A, sorry, which is equal to the probability of omega I1 given A plus the probability of omega I2 given A times, etc., plus the probability of omega I K given A. So now, here I'm summing the probability of omega I1 divided by the probability of A if omega I1 is in A. Otherwise, I sum 0. So let me put it here, something like that to remember it. Well, okay, this needs some notation which probably you are not familiar with. So this function here is 0 if omega I is in A, is not in A, sorry. 1 if omega I is in A. So I'm summing these functions here. And what do you obtain at the end? Probably these computations are better done by oneself. But if you want me to repeat them, please simply ask me. But what do we obtain at the end? That the probability of E given A is equal to the probability of E intersected to A. Why? Because we are summing only over those omegas which are in A and in E, and then divided by the probability of A. Why? Because if we come back, everything is divided by the probability of A. So at the end of the day, we obtain this expression, which is the one you find in textbooks. So this is the only way which is it makes sense to do a conditional probability. And let me repeat, how do we obtain it? Well, we have a complement. We know that A happened, so that we simply erase what is outside A. And now our new word is simply, sorry, our new word is simply A now. And we have kind we have forgotten about what was here. So here we have our P, but now our P is not anymore of mass 1 here. So we have to normalize it by dividing by the probability of A. So this is equal to Q. And it's a probability here. And it maintains the proportions. It keeps given by P. But of course, we are forgetting one part of the image. So this is graphically, it's very simple actually. So it is simply removing one piece of uh, the let's say of the sample space. Now maybe let's do an exercise simply to check the definition. I recall the definition here. So the probability of E given A is equal to the probability of E intersected A divided by the probability of A. Okay, so let's make an exercise, and then maybe I will do an example which is a little bit more interesting than the exercise, because the exercise is only to check the definition. So let me take it, which it was probably this one. So the exercise number 3 of the file that I have sent you. So maybe let's correct it in 10 minutes. So since you should have it, maybe let me, in the meanwhile, write the definition here of conditional probabilities. So it's in the chat of the file. Um, so, can we correct it, or do you need more time? Maybe let's do them together, so I can maybe have some more time to tell something more. So I was trying to list all the elements, but it was a task which is quite, I mean, requires some little bit more concentration, and I think that I've lost myself, but it can be done without listing all the elements. So let me simply go here and try to solve it. So the sample space is is the space of triples. So is the space of simply of triples like 1, 1, 1, 1, 2, 3, 1, 1, 1, 2, etc., until 666. So this, the number of elements of this space is quite big. It is equal to 6 to the power of 3, which is 36 times 6, which is a big number. And the event A that we know it happened is that no two faces show the same number. I guess if this is the text. Let me see. No two faces show. Sorry, no two dice show the same faces. So what is the probability of finding two aces? So no two faces show the same number of elements. No two dice show the same faces. So and B is equal to the set that two aces. Sorry, no. The probability of mm, okay. Let me see if I copied the test correctly. So um, okay, I mixed two exercises, sorry. Of course, this is 0, so I was quite sloppy. So the probability of two or more aces, I mean, the solution of this exercise is quite easy because the intersection of A and B is equal to 0, to the void set. So simply when you go and compute B given A, this is equal to the fraction of and this is equal to 0. So, I mean, you should have told me that, okay, this is, there is something wrong with the exercise. Actually, what I wanted, what the test, I mixed two exercises, but what the text wanted to compute is the probability of 1/8. Now, so what is the probability of 1/8? Well, of course, okay, here we put the uniform probability because we are assuming like that the dice are balanced. So the dice are balanced. So that we put the uniform probability. There is no favorite outcome. So how many elements, elementary events has the sorry, let me first, so let's first try to compute this quantity here and see if we can simplify it. This is equal to the probability of the intersection divided by the probability of A. But this is by definition. Now we can use the definition of uniform probability to see that this is equal to, well, the number of elements of B intersected A divided by the number of elements of omega. This is to what is equal the numerator. The denominator is equal to the number of elements of A divided by the number of elements of omega. So it's equal to this one. Now, well, the number of elements of omega simplifies. But, okay. The screen is not really sharing. So, I mean, are you still there? Mm.
Well, it's still the board and
Ah,
there's your cursor, and yeah, it is like this.
okay, sorry, I didn't share my desktop, but only the board. So I was writing it here. So, I, I was writing the sample space here, omega is equal to the set of triples of the results of the dice, plus 6 to the power 3 elements. So the dice are balanced, so we put the uniform probability in it. A is the event that no two dice show the same face, and B is the event that two or more aces are present. But now A and B is impossible, so this probability is 0. So the exercise was mixed up with another one, so this is not the correct the thing that I want to ask. So the probability of 1/8, I want to ask this one. So before everything, what I did is to compute the definition of conditional probability. Then I use the definition of uniform probability to write this one. The probability of B and A is equal to the number of elements of B and A divided by the number of elements of omega, and the probability of A is equal to the number of elements of A divided by the number of elements of omega. Now, the number of elements of omega simplifies now. So we can simply write that the probability of B given A is equal to the probability to the probability of sorry, to the number of elements of B and A divided by the number of elements of A. And this here I didn't use in any by any means anything, only that the probability is uniform. Well, now we have to compute to compute simply the cardinality of these sets. How many elements does it have? Well, how many elements A has? Well, we can choose the first die between 6 elements, the second one between 5, and the third one between 4. So it is like 6 times 4, 5 times 5 times 4, which is equal to 4 times 5 is 20, 20 times 6 is 120. So this is the cardinality of A. Then how many elements that do contain an ace, or maybe it is better to do the opposite. So how many elements in A that they do not contain an ace? So let's compute this cardinality. It's better, it's easier. This is equal to the set, to the elements in A, the number of elements in A that do not contain an ace. So, well, this is again easy because we have to choose the first dice between 5, then between the other one between 4, because we cannot choose twice the same face, and then the last one is between 3 elements. So this is equal to 20 times 3, which is 60. And therefore, the probability of B given A, of this second choice to see an ace given that the faces are all this different, is equal to the probability of the number of elements of B and A divided by the number of elements of A, which is equal to 1 minus the number of elements of that are not in B but are in A divided by the number of elements of A, which is equal to 1 minus 60 divided by 120, which is equal to 1/2. So this is the solution of the exercise. It is not deep. It is not deep. It is simply a computation, but is to check the definition. Just that. So maybe let me finish. So do you have questions concerning this exercise?
No?
Okay, so it's simply a definition. So let me finish with an example which is a little bit creepy, but it is actually it actually happened for real. So it is a real judicial case, which actually probability is quite is being used to try to do some automatic I don't know, some automatic judges that you give them inputs and they tell you if a person is guilty or not. But in any case, odds are always considered when in a judicial case. So what happened is that the following. So a woman has been killed, and the first I don't know, first one, I don't know, the one who is believed to have killed her.
Suspect.
Thank you. The first suspect is the husband. So it turns out during investigations that he beated her. He usually beated her, and of course this is a proof against the husband. So the defensor argued the liar argued that bringing statistics into the case, the statistics show that only like 1 out of 10,000 men that beat their wives end up killing them, arguing that this was not a strong hint into, and argued that this is not sufficient to say that to conclude that the husband is the culprit. So this actually is of course is not so there is a fallacy. There is a fallacy in the arguments. Because that 1/100, what does it mean? It is the probability. Okay, let me write the things in a good way. So A is equal to the event the husband killed her wife, killed the woman, and B is the event the husband beated his wife. So and the event, so what that statistics tells you is that 1/10,000 is equal to the probability that of A given B is equal to this number, 1/. But actually, if we go and draw some lines like I don't know, in the blackboard, so here. So what is he telling you is that if B, so if B is the event that an husband beats her wife, so he beated her, is that only one over a small portion of it is the event that so, and this is the event A, for instance. The husband killed her wife, his wife. It tells you that this percentage, like it tells you that if we consider only B, it is a really small portion of B, this one. So if we forget about this part. But actually, we know much more. We are omitting like the most important detail, which is that we also know C, that the girl, the woman died. So we know B and C. So we don't have all of this space here. Here we have like I don't know. We have C, for instance, is this one C. Let me paint it in green, no, in red. So maybe C is the event that the woman died, and maybe is the following, like this one. So we know B and C, if we go here and zoom it, well, this one is like, I don't know how can I draw it. So here is B and C. No, sorry, here is, this one is B and C. And this is A and B and C. So there is the proportion is much bigger here of the event A. So you see, removing like the proportions can change a lot if we remove. So if we forget an event, actually an event, the most important here in a judicial case, that there was a victim. So something happened. This really changes a lot the proportions. And what we will do now, if there is time, is to see this in formulas. Actually, it's very easy to compute. I mean, probabilities are quite linear, so they are very easy to compute. So maybe let's, I don't know what time is it. If there is some time, we will see this by doing some two computations, and then we will see next week. So yes, there are 5 minutes. So the fallacy is that we are forgetting the most important event, that C, which is C, that the woman died. So let's do some computations, and let's see what really what's about this. I mean, this data is right. So this P, the probability of A given B that is estimated by this number, it's okay. But now we have to compute this probability, the probability of A given B and C. This is equal to the probability of A and B and C divided by the probability of B and C. Now, so we can write C as the event that C is equal to the event A that so that his husband killed her plus the event that another one killed her. So C Z minus A. So we can use this decomposition. So the first set is that his husband killed her, and the other one is that another one killed her. So we can use now this decomposition to write this equality. So A is contained in C because yes, because A is the event that the husband killed the woman, and C is the event that the woman died. So on the numerator we have A cap the U and the B. While in the denominator we can use the additivity to write it as the sum of A and B and A plus the probability of B and the complementary of that somebody else killed her. So something like this. Well, now we simply take a common as a common factor this probability of A and B. So this is equal to 1 divided by 1 plus the fraction of the probability that somebody else killed her divided by the probability that on B her husband killed her. So you see, actually, what does it matter? It doesn't matter this. So let me give a successive passage. So this is equal to the. This can be. I mean, it's easier. It's a matter of computation. You can easily see that this is equal to the. Now we we multiply and divide by the probability of B, and this is equal to the probability of that somebody else killed her divided. So the event C is actually that the woman was killed, because we know that it was killed. Otherwise, there would be less evidence. against her husband. So multiplying and dividing by b, we obtain this expression at the end of the day. So you see that actually, not C, but A. It is not what matters, but it does matter is not the probability of A given B, but but rather its ratio against the complementary event. So there's something called, usually they're called the odds. So it matters like this one, uh, this ratio here. And so um, his argument doesn't mean anything because you have to go here to the where is sharing? Okay, you have to go here, and you have the event that the husband beats his wife. So the event C that a woman was killed. This is C, and here you have the case in which A, it happens A. So even if A is small compared to B, it is not small compared to B in C. So the probability of C minus A given B divided by the probability of A given B, it looks very small. So it could be like 0.1. So if we go there, we see that the probability of A given B and C, if this is the number, probably maybe in the next lecture I will start by estimate this quantity here on this part, but this is 1 divided by 1 plus 0.1, which is equal to 1 divided by 1.1, which is much bigger than, I don't know how much is it, but is like close to 1. Like it will be bigger than 0.9, I guess. So I mean, this is a fallacy in judicial proofs that mean, okay. So it was not so clear, but I will start the next lecture with this example again. So I will send you tonight the exercises for the next week and correct the ones that are left. So thank you for, I mean, have a nice večer, a nice night, and see you next week. Of course, if you have questions, you can write me. So goodbye.
Thank you. Goodbye.
Goodbye.
Thank you. Goodbye.